Dear students, welcome to the lecture series on power system analysis. Today we will be discussing about dynamics of synchronous machines. So here we are trying to understand how the rotor of synchronous machine behaves during different operating conditions. So here we are trying to express such behavior in terms of some equations, and we'll be seeing such equations in details. Now the kinetic energy that is being received at the rotor is being available to the rotor from the mechanical input that is being fed into the rotor. Okay, so that mechanical input is converted to kinetic energy, and that kinetic energy further within the interaction of the magnetic and electric fields, it will be converted to electrical energy, and you will be getting electrical energy at the output. Okay, so that is given by EV by X sin delta. Now the kinetic energy that is being generated at the rotor of the alternator or the motor is given by half J omega Sm square, where J is the moment of inertia in kilogram per meter square and omega Sm is the synchronous speed in mechanical radians per second. Now you can convert your mechanical radians per second, that is omega Sm to omega S, by using the general equation theta m is equal to 2 by p into theta e, where theta m is some mechanical angle and theta is the electrical equivalent. So once you differentiate it, you will be getting omega Sm equal to 2 by p into omega S, where omega S is represented in electrical radians per second. Now once you replace your omega Sm with omega S, we will be arriving at this equation, that is 2 by p the whole squared. You will be replacing omega Sm with omega S, so that is 2 by p the whole squared into omega S the squared. So this particular term, kinetic energy equivalent to half J into 2 by p the whole square into omega S squared. So J into 2 by p the whole square into omega S can be written as M, where M is the moment of inertia expressed in megajoules second per electrical radian. So your M is J into 2 by p squared omega S. Okay, and again M also can be written as 2 into kinetic energy by omega S. So from this you will be arriving at this unit. The unit of kinetic energy is megajoules and omega S is expressed in electrical radians per second. So these units are very important from numerical perspective. You will be getting few questions from this topic, numerical problems. So in such a case, here itself we can see that you have moment of inertia expressed in megajoule second per electrical radian, which is denoted by M, and J is another term which is also a moment of inertia expressed in kilogram per meter square. So you have to identify these terms with the units. So units are important. Now your kinetic energy also can be expressed as G into H, where H is the inertia constant in megajoule per MVA or megawatt second per MVA, and G is your three-phase base MVA. Now equating your two equations, that is kinetic energy equations. Equation 1 is this one, kinetic energy is equal to half m omega S. So when you are equating these two, you will be getting half m omega S is equal to GH. From the equation you will be getting m is equal to 2GH by omega S, where you can replace omega S with 2 pi f. So you will be getting GH by pi f, and the unit is megajoule second per electrical radians. Again this can be expressed as GH by m is equal to GH by 180 f. Then the unit becomes megajoule second per electrical degrees. Now once you divide this m with G, you will be converting it into per unit, since G is your base MVA. So you will be getting H by pi f. M is equal to M per unit is equal to H by pi f. So the unit will be second squared per electrical radian. So that comes from this equation, megawatt seconds per MVA. Okay, so when you are replacing this megawatt, you will have second left over. So that second will be multiplied with seconds per electrical radian. So we will have second square. So we will have the unit m is equal to h by pi f. Now this inertia constant is a very important term, okay, from a practical perspective. Generally the values of this inertia constants varies from 2 to 9. Okay, so 9 is generally for steam turbine coupled synchronous machines. Okay, steam turbine coupled generators. Okay, and the value for a hydro generator, it will be in the range of 4. Okay, for hydro. Now the importance is that once you have a value of 9, that simply means that your system is having a larger inertia available, or larger amount of capacity to store the energy in the rotating mass. Okay, so that stored energy is being converted into electrical energy. Now this hydro is having a lesser value, so your steam turbine coupled generator or turbo generator, steam turbo generator, will be having a higher value of inertia constant, and it is able to supply more power during disturbance. If there is a requirement for electrical energy, the kinetic energy can be converted to electrical energy, so more kinetic energy can be stored in the rotating mass for a turbo generator from a steam turbine system when compared to a hydro generator. Now these values are important from a practical perspective, where we are trying to add more solar type of resources. Okay, where there is no inertia term associated with solar energy, because everything is a static device. There is no rotating mass available with the solar. So once you are trying to add more solar system into the power system, or solar generators into the power system, whenever a solar fails, it has to be, that failure of the solar has to be absorbed by some rotating mass. Some 100 kilowatt is failing, so that much energy has to be supplied suddenly from a rotating mass. So in such a case, these rotating kind of machines, okay, or generators will come to the support. In such cases, this steam turbine coupled generator or hydro generator will be useful in order to supply that excess required energy, okay, which comes due to the failure of such renewable sources. Okay, so that is one of the issues associated with the renewable sources, and generally what you do is that you will be adding some dummy machines, which will simply act as a storage for this energy, just to act as an storage for or supplier for kinetic energy. Okay, once your system fails, so kinetic energy has to be stored in order to supply it during your required periods. In such cases where you have some failure of some of the systems, once a entire generator fails, so that excess load has to be shared among all the other generators. So in such cases, generators which are having larger inertia constant will have the responsibility to share a larger load. So in such way, the load will be shared among different generators. Okay, so this inertia constant is very important from that perspective. Okay, now these equations are important once you are trying to derive a swing equation for these alternators. So the next topic is swing equation. So in that we'll further see how your rotor angle is varying with respect to different disturbing situations. Okay, so thank you.